All right, welcome. In this video, we will take a look at our full system implementation of a input signal coming in to our STM32 F7 Nucleo-144 board through an ADC channel. We'll process that signal, we'll grab that signal and then do some processing on it. In this case, we'll basically spit it out back on the DAC. Uh, so we'll grab the data from a ADC channel into a processing function that we'll write, and then the result of that processing function will be sent out via the D to A converter. In the past, we've seen the use of ADC and the DAC hardware, either using the polling method, or we've seen an ADC conversion interrupt. And then we've also seen how to do a precise sampled ADC using a timer and a timer interrupt before. Today's video, we will deviate from that a little bit. And what we'll do is we'll use a timer controlled ADC and a DAC, but we'll use the timer's trigger output to trigger the ADC and the DAC hardware. We'll also, instead of using polling or interrupt, to move the data from the ADC data register to a memory, and later on from a data memory into the DAC's uh, uh, data register. Instead of doing that using the CPU clock cycles, what we'll do is we'll instead use a direct memory access engine. So we'll use the DMA to basically transfer data from the ADC data register into a input buffer. We'll do some processing on that input buffer and move the output buffer into DAC via DMA. So here's our overall system setup. So you see, so here's our overall system setup. So here it is, a block diagram. ADC comes in, so the signal is coming through via the ADC channel. The ADC will be triggered by a timer. We'll set up a timer for a specific frequency that we want to use. The ADC will be triggered. The ADC data register will be transferred to a input buffer, ADC buffer, using the DMA. When the DMA does the transfer, it generates two interrupts. One when half of the buffer is full, and one when the full buffer is full. So let's say if we decide that the buffer is 100 spaces right here, after 50 spaces have been filled, the half transfer complete flag goes high, and it can generate an interrupt. After the full buffer has been full, all 100 entries have been filled, the full transfer complete full transfer complete flag will be raised. Now, one advantage of using this is we can set up a system where instead of waiting for the entire ADC buffer to fill, what we can do is have the DMA move data from the ADC into the upper half first. While this upper half is being filled, the lower half of the ADC buffer will be processed by our function. Here I call it a generic process underscore data function, but this is our function that's going to process data. Maybe it's a FIR filter, maybe it's taking the square root of a signal, maybe it is doing something else. So the lower buffer is being processed while the DMA is filling the upper buffer. So when the upper buffer is filled, the DMA will turn this flag on. When this flag turns on, we'll switch over the DMA filling to the lower half, and then we'll start processing what is new data coming in the upper half. Now, when we do that, once we have the upper half of the data being processed, well, the processed data has to be stored into the DAC buffer. Again, we'll do the exact same things because the DMA is moving data from the DAC buffer. Again, this is just a memory. So if we had 100 spaces right here, let's say while it's being processed, it was filling the lower half, so that means the upper half can be emptied by the DMA into the DAC. So this way, we'll get a much better control of our data flow, and we will also free up the processor cycle by not involving the CPU itself in the movement of data from the ADC data register into a memory or from the memory to a DAC data register. Because every time a CPU has to do that, you would have to load data and store data. So there's a load and the store cycle involved. And in this case, we're basically freeing the processor from that. So this is the system we want to implement. Okay, so let's go ahead and do that. Now, in order to do this, we'll again use the STM32 CubeMX to do this. So let me launch STM32 CubeMX. And what we'll do is the following setup. We'll set up ADC 1 channel. In the Nucleo board, I want to put in my data going into port A0 in the CN9 connector. So port A0 in the CN9 connector belongs to ADC 1, 2, and 3. So there are 3 separate ADCs, but it belongs to ADC 1, 2, 3 channel number 3. Again, there's about a lot more channels than just 3 here, but I just show you a snippet of that. So ADC1 channel 3 will be our ADC, this particular ADC hardware. Now, moving on to the DAC side of things, we'll use the DAC output 1. DAC output 1 is on CN7 connector, pin 17. Again, you can find all of this information as to where certain pins are located on the Nucleo-144 reference board reference manual. So we have the DAC and the ADC set up. We want to do the debugging using our serial port. So we'll have to, we'll want to do the debugging using serial wire. So we'll have to set that up. And finally, we want a timer control ADC1 and DAC. We have number of options per timer. There's no reason why I enable timer 6. The real reason is that its timer 6 is a fairly simple generic timer. It's a 16-bit timer with limited functionality. The other timers, for example, timer 4, timer 2, those timers can do a lot more, like PWM generation, input capture, output compare, those one-shot, those kind of things. Timer 6 is fairly simple. It's a 16-bit timer. Activating it is fairly easy. You just click on activate there. So when all of this is done, this is what my chip looks like. I have the serial wire debug channels right here. The ADC in is in port A pin 3, PA3, which happens to be mapped to the CN9 connector to A0 on the Arduino headers on the Nucleo-144 board. And similarly, when I select DAC output 1 configuration, it is located on port A pin 4, PA4. Now on the Nucleo board, when you search for PA4, you see that it's actually mapped to an SPI line, but it doesn't matter. We're mapping that to the DAC, and that particular pin, the PA4, according to the Nucleo manual, comes out on the CN7 connector, pin 17. So I'll be putting in data from the waveform generator into PA0, PA3 pin, and looking and probing the PA4 pin with my oscilloscope. Okay, like what we've done on every single project. Now let's do the clock configuration. And the clock configuration we're going to do is basically a 216 megahertz clock, which automatically, of course, sets up the different peripheral bus timer clock. So in our case, timer 6 is located on the APB1 bus. If you want to find out exactly where the peripherals are located, you can look up on the STM32 F7 reference manual. So if you look up the reference manual at the very beginning of the manual on a memory map data, you'll find which peripherals are located on what bus. So APB1 bus is where the peripherals are, the timer 6 is located, so it's getting 108 megahertz. Also, remember that the Nucleo board does not have a external crystal, so it's taking the 16 megahertz internal RC oscillator, sending it through a PLL, and generating this 216 megahertz. It's good enough for our purpose now. So once the clock is configured, let's go and configure our different peripherals. So here is our peripherals that we want to configure. So let's start with our controlling peripheral. Since timer 6 is designed to control both the ADC and the DAC, so we want a specific frequency on timer 6 to be able to do that. So let's double click on timer 6. It brings up this particular configuration, by default, the counter period is set to 0. I've added 1124. I'll get to that in just a second as to why 1124. But the next thing I want to see is that make sure the trigger output event TRZO. So the TRZO, the trigger output, can directly enable ADC and DAC when connected, okay, to them. So we want to make sure that that is set up to an update event. So we want to wake up the ADC and the DAC and say collect data whenever this timer update event happens and is triggered. Now let's go back to the 1124. So we wanted to calculate, we want to be able to grab data from the ADC and send data out on the DAC at a specific timed interval. Because since we're doing DSP, we want precise control of our sampling rate. So in my case, I decided I wanted a 96 kilohertz sampling rate. So that's 96 kilohertz sampling rate is what I would really like. But I can't enter 96 kilohertz here. So what I do is if I want to find out what the value of the auto reload register is. And in our case, we're adding a prescaler of 0. So that means the clock that is coming in from the APP bus, APP1 bus, which was 108 megahertz, is the exact clock. It is not being prescaled. It's not being the frequency of that clock is not being divided. If I had put in a 1 on the prescaler there, so if I had put in a 1 here, that means the 108 megahertz APP1 clock would be divided by 2. And that divided clock is what would trigger the counter, that freely running counter that's embedded in the timer 6 hardware module. In our case, since the prescaler is 0, our counter connected to timer 6 is actually counting and getting a clock frequency of exactly 108 megahertz. So the counter is going to update itself 108 megahertz. So that means I'm going to get 108 million edges in 1 second. What I really want is 96,000 edges every second because I want to do a 96 kilohertz sampling rate. So if I divide 108 megahertz by 96 kilohertz, what I get is the value that I should put in the ARR register plus 1. So ARR plus 1 is equal to 108 megahertz divided by 96 kilohertz, which basically gives me ARR to be 1124. So that's how I got the count of 1124. Let's move on. So that's all the settings we need. We don't need to have the timer 6 interrupt enabled in this case. In the prior video, I showed you how to do a precise control using the interrupt of the timer 6 or timer 4. But in this case, what we want to do is directly use the TRZO output of the timer to trigger the ADC. We don't want to trigger the ADC in software by saying ADC start, HAL ADC start, or HAL DAC start. We don't want to do that. We want to automatically trigger it using the timer. So we won't be setting up the NVIC. So this timer will generate a update trigger output every 96 kilohertz. So 96,000 times a second. Now let's move on and look at the ADC settings. On the ADC side of things, so after the timer, if I move on to the ADC side of things and look at the ADC configuration. So this is the first place I want to look at. In our case, we'll leave the clock prescaler default. You could change the resolution if you wanted. I left it at 12 bits. So that means we'll be getting ADC values mapped on the analog side between 0 and 3 volts. Should show up on our digital side mapped to 0 to 4095. Data alignment right, all of those are by default. So I've changed nothing at all here. The only thing I changed was instead of external trigger convergence source, we used to say convert using software trigger. In this case, I've added the timer 6 trigger output event, and I said the timer should be detected on the rising edge. So that's the only change here under configuration. Now let's go and look at our DMA settings, because what we want to do is we want to offload the task of moving information from the ADC data register we want to offload that responsibility from the CPU to the DMA engine. So what we want is the DMA controller. The DMA controller is connected to the higher bandwidth bus called the AHB bus. It basically allows data computation and transfer to take place in parallel with any other computation that the CPU might be doing. So let's say the CPU, we put something in its while one loop in main. The CPU could be executing what's in while one loop in main without having to worry about going and grabbing information from the ADC register into the buffer or from buffer into the DAC. Okay, what this basically means is that we'll get a significant boost in the overall performance of our system. And that's what we want, because we want to be spending more time processing our signal than in the auxiliary task of grabbing our data from the input and sending our data towards the output from the ADC and the DAC channels. Okay, so we've offloaded that to the DMA. So let's go look at the DMA settings for this case. On the DMA settings, now go and so under QMX on the DMA settings, ADC1 ADC1 is connected to a DMA2 engine stream 0. In this case, we want our ADC, which is peripheral data register, to write its value, or the DMA to take the data from the data register of the ADC, which is a peripheral, and store it in an array which is in memory. So hence we say the direction is peripheral to memory. Let's give it a high priority. You could leave it a low priority. We're not using any other DMA for our purpose. The only DMA request we're going to make is to the ADC, and we're going to make another DMA request to the DAC, and they actually are in two separate DMA hardwares. So in this case, you could leave the priority to low, but in this case, I just created a high. Every time a data is written to a memory address, we want to automatically increment the memory address. So let's say at first DMA moved data into index 0 of an array. We want next time the DMA to put the data into index 1. So we automatically want to increment the address of the memory side. On the peripheral, there's only one ADC data register. We don't have to increment the address of that. Okay, so we'll leave that checked into memory. Now, what we want to do is we could have left it as half word, but I decided just to put in word for here. So the data width that we're going to move at a time is a word. Mode. Under mode, here's I click on circular mode. What that basically means is that the Dma circular mode is basically, it allows the processor to reuse the ADC result array. So for example, if my ADC buffer was called, I don't know, ADC underscore val. Let's say that was the name of my buffer. If the ADC underscore val fills up at the end, we would get a error if the DMA had to bring in a new data value. However, with circular mode, what happens is once that it gets to the end, the DMA will go back and start at the top and repeatedly filling up this of the data. So basically, to summarize, the circular mode basically allows the processor to reuse the ADC result array, which I called ADC underscore val just now, repeatedly during each sequence of the ADC conversion, so that we're not overrunning the memory that we had set. So one thing to keep in mind, if you look at the STM32 F7 manual on DMAs, you'll find there's a number of streams of the DMA. So it's not just the ADC one, which is on the APB bus. That could request a DMA. We might have a UART doing a DMA to move data from a serial port to a memory, or from memory to a serial port, and all that kind of stuff. So there are different streams you could select. ADC1 happens to be on stream 0. Okay, so those are just a few things to play with, and that's basically all the DMA setting we need to do. Let's say okay, and move on. So the next thing, so we've set the parameter. So we've set the parameter of the ADC to be triggered by timer 6. We've set the DMA to move data from peripheral to memory. Some of the key things we changed was we've auto incremented the memory address so that we don't have to explicitly go and change the array index, as the DMA engine is taking care of this. We asked it to move a word. We could have said half word instead of a word, but in this case we asked it to move a word. And then this is important. If we don't want the DMA to be completely, once the buffer is full, we want it to be able to repeatedly fill the buffer from top to bottom and go top to bottom, top to bottom. In that kind of mode is called the circular mode. So that's what we've done so far. As soon as we enable the DMA, now let's go check out Nvic settings. We're not going to be asking ADC to generate an interrupt. Okay, we're not going to be doing that. But as soon as we enable DMA, a DMA stream interrupt gets enabled by default. So if you look up here, the ADC1, ADC2, and ADC3 global interrupts. Before, when we did ADC interrupt-based ADC, we manually checked that. In this case, we're using the DMA to do all the moving, so we're not going to do that. So by default, as soon as we enable the DMA2 stream 04 and connected it to ADC1, by default, this has come in checked. So we don't have the option. We don't have the option to disable that. So it's automatically enabled once the DMA is set, right? And we don't need to enable the ADC1 global interrupts. Okay, let's move on. Next item. So ADC is fully configured now. So the next thing we want to configure is the DAC. So DAC, let's click on that. So we'll click on the DAC, and that will bring up our overall DAC configuration. Now, simple change we want to make. The output buffer should be enabled. The trigger in this case again should be the timer 6 trigger out event, not software. Timer 6 trigger out event, and the other wave generation we will just disable. We're not using the DAC to do a specific kind of generation of a triangle wave or a noise signal and so forth. You can find out more about that wave generation mode if you read up the STM32 F7 reference manual on the DMA again. Okay, so that's what I have set up so far. Now let's go and take a look at, so in this case we don't have to do anything specific on the Nvic settings. No nested vector interrupt controllers are required yet. Let's do the setup for the DMA because that's what we want. So when we click on DMA, so I've selected DAC1 here. So what we'll do is set up the DAC1 right here. We'll set up the DMA1 stream 5 by default. Now if you think about the digital to analog converter, it is grabbing data from a memory array and sending it to the data register of the DAC1 and saying, I'm done, send it out. So we're moving data from memory to peripheral in this case. Again, when we do movement from memory to peripheral, we want to automatically increment the index of the array so that after index 0 has been moved, the next time around when things are moved by the DMA, it should be from index 1 and so forth. So here it is. So memory, I've set the increment address, and like I mentioned during our ADC setup, the mode for the DMA should be set to circular. Say OK to this. Oh, actually, before you do that, let's take a look at the Nvic settings again, just like the ADC. As soon as we enable the DMA 1 stream 5 global interrupt line is actually enabled. So that's actually enabled right here. And we don't need to do the timer 6 global interrupt, DAC1 and DAC2 underrun error interrupt. We won't be setting that up for now. So that basically is all we need. So the DMA interrupt is automatically set. We can't change that. We don't need to set up anything else. The next thing we're going to do then is basically we've set up all the configurations here. So we'll basically go to project settings. We'll choose the correct tool chain. So in our case, we're using Keil MicroVision, so MDK ARM v5. And basically on the code generator, next step, I like to do this all the time, copy only the necessary library files. By default, it says copy all used library files, but all my projects, I do only copy only the necessary library files. And then finally, to make sure that the main.c file is not cluttered with all initializations in a single file, I ask the generate peripheral initialization to be set up as a pair of .c and .h files. So once that's all done, I'll say OK to this. And basically generate my code. Once the code is generated, it'll ask me to go and open up a project on Keil Microvision. So let's do that. So let me go and open up my Keil Microvision. All right, so open up my Keil Microvision project. So here it is. It's coming up. All right, so let's take a look at this particular project. So I have the ADC, the DAC, and the timer main peripheral. So if you look at the right-hand side, or sorry, left-hand side window, I have the ADC, the DAC, the timer, and the DMA now enabled. We can look at the different functions available here. Remember this file right here, the _IT file lists all the functions that are related with the different interrupts that are set up. In our case, we only have the DMA1 stream handler and the DMA2 stream handler. You can browse through what these functions do. Functions do by basically first time you want to do that, you will have to build the code. But then after that, you can right click and basically say go to the definition of what these IRQ handlers do and so forth. So that's what we'll do next. So I'm going to let this system build first so that I can browse around my code a little easier, and then I will add that as part 2 to this particular video.